Hi everyone, welcome back to Requirements Engineering. This time our topic is quality assurance, and let me quickly walk you through those slides here. So let's start with a little Dilbert. We all know it's not that funny because there is a lot of truth in the comics, I guess, but this one is particularly about quality assurance. So he's offering Ratbert to get hired for the quality assurance group. He said you'd be perfect. And Ratbert says, "What would I have to do?" "Oh, you would find flaws in our new product, thus making yourself an object of intense hatred and ridicule." And Ratbert says, "But then you'd fix those flaws, and you'd respect me for... Your respect for me will grow into a special bond of friendship, right?" "Nope, then we ship." So we see in this little comic already what one of the troubles with quality assurance is. So it often happens towards the end of the development life cycle and does not get completed in its feedback loop into the product. Today, I want to briefly introduce the foundations of quality assurance to you. What are quality criteria for requirements engineering? What is constructive and what is analytical quality assurance? What is quality assurance for artifacts? And then what are techniques for quality assurance? So first, motivation terminology. Then what does quality for requirements documents mean? What are principles of quality assurance? And then a couple of example techniques for constructive and analytical quality assurance. To briefly remind us, what are the biggest problems in requirements engineering? Most of them incomplete and hidden requirements, and those can be very well detected by using quality assurance techniques. One of the many of them is in this example. So your users can only delete posts when logged in. Yep, yeah, correct. And then on the right side, you see the implementation. You cannot create a new post while logged in. You may only delete them. Well, that is obviously not what we meant. And so we see the red only on the left side having a different emphasis than how it is being implemented on the right. So what does that mean for us as requirements engineers? When we talk about quality assurance in RE, we usually talk about quality defects, and we talk about incorrect requirements. So we have invalid, incorrect requirements that do not reflect the intention of the stakeholder, or we have quality defects, requirements that are in themselves valid requirements, but they have qualitative defects. So they either miss the measurability, they are hard to understand, they contradict each other, or we may have a combination of those two. So incorrect requirements are often hidden due to quality defects, and the correctness of requirements is often viewed as a quality criterion as well. And for that reason, we perform validation and verification. So validation is where we check the requirements with regard to correctness, and verification is to check whether the system fulfills the requirements, and both are part of quality assurance. Quality assurance in requirements engineering specifically means the application of systematic measures for identifying quality defects and assuring the quality of requirement specifications. This is according to the IEEE recommended practice for software requirement specifications. They check for quality criteria, for example, correctness, completeness, consistency, and traceability. You'll see a more complete list on the following slide. And that examination can be conducted constructive or analytical. Now, for the quality of requirements documents, we know a requirement is a demanded characteristic of a system or process, and we distinguish a syntactic representation in form of a text table, diagram, or formula, and a semantic representation, content, informal or formal. And then a requirements document can have a number of requirements, and it also has a structure. Now we delimit that from a requirements repository that serves for storing large sets of requirements. as opposed to just a list. For the quality assurance of requirements documents, we already have an understanding that this is crucial, but why is it so important? We need to understand what those documents are further used for. So down in this comic, the boss says, after apparently hiring Ratbird, that in the short time you worked in quality assurance, you found a huge number of flaws in our prototype. That's my job. You're jeopardizing our schedule. The entire project will fail and it's your fault. Why is it my fault? If a tree falls in the forest and we've already sold the tree, does the tree have quality? How many angels can dance on your head? So quality assurance often gets a bad rep because they slow down the process, whereas in fact the process is being slowed down by errors that were produced earlier. And luckily they were caught before the product was shipped. So we distinguish as perspectives in quality assurance and requirements engineering the one of requirements documents versus sets of requirements inside those documents versus individual requirements versus then verifying that it's actually happening in the system. The principles of quality assurance, they are two-faced, constructive and analytical. So when project team members with domain knowledge apply that knowledge during the elaboration of the requirements, for example, when they pay attention to correctness, then that is called constructive quality assurance. Whereas when an external, neutral quality responsible who performs checks for, say, traceability and understandability, that is called analytical quality assurance. So constructive happens while we engineer the thing. Analytical happens after we're done with the full draft. And here we see a coarse-grained overview of quality assurance guidelines in constructive and analytical, or quality assurance techniques, I should say. And not all of it is necessarily for requirements engineering. A few are more specific to later implementation phases, but just to give you a general idea. So things that are constructive are process standards like quality criteria and linguistic rules. We have programming guidelines, so those programming guidelines, they are for the later phases, but we certainly have a lot of process standards in requirements engineering. And then on the analytical side, we have analysis using metrics or anomaly analysis tools or graphics. We have testing, dynamic, static, reviews, and we have verification, either formal or model checking. And I'm sure you've heard about a few of them in earlier courses. Now for constructive, what we like to use are reference models, the quality criteria according to IEEE 830, linguistic guidelines, and general guidelines. Reference models are, for example, our MDIR artifact model, where I would check whether it follows the guidance of the reference model. Then the IEEE 830 recommendation on software requirement specifications, the Coburn template that we've seen for individual requirements, for individual use cases to be precise, and then the UML2 standard, where I can check whether diagrams conform to the standard. For the IEEE 830 standard, we have a list of quality criteria. Completeness. Systematically run through all the cases that you possibly can in your system. But careful, you cannot actually find that the system is complete. You can only find that it's incomplete. So it's like debugging. Consistency. You have to relate everything back to one system model. You may have a behavioral view and a static view and a function view, and they should all be able to be mapped onto each other. For unambiguity, we can check the phrasing. For correctness, we validate. For structuredness, we examine the structure, whether it's according to a certain either standard specification or whether it's just in general well understandable. And then traceability, are requirements sufficiently linked? Changeability, can expected changes in requirements be conducted efficiently? For understandability, we have to check the phrasing, the formulations of the requirements, and then the agreed uponness, we have to check with the stakeholder. What you now do with this checklist from the standard is you take it and you make your own questions for the type of document, of requirements document that you have to review. And you can be inspired by the questions before, but you have to come up with your own version if you use a different type of specification or according to the type of specification that you use. So I suggest to pause the video here for a moment and try do that for the work that we've been doing in this course for the set of artifacts. All right, we're back. So as an example, you can, for a simple spreadsheet with requirements, let's take a really simple approach to requirements engineering. We just have all of them in one spreadsheet. Say for completeness, we're just going to read through and then ask, are there still open questions from the lead engineer, from the stakeholder, from the customer? We can check consistency in terms of checking for requirements conflicts. We can make a language check for unambiguity by letting someone else read it and check whether it could be misunderstood. For correctness, we can check with the stakeholder. For structuredness, we check whether it adheres to the template or outline and whether it has a breakdown that makes sense. For traceability, we check links between requirements in the spreadsheet and across versions of the spreadsheet. Changeability then checks dependencies between the requirements. So a high degree of dependencies means a rather low changeability because it just makes it tough to be consistent. And then understandability is checked by letting someone else read it, whether it's easy to understand. Agreed uponness, again, we got to check with the stakeholders. For linguistics, there are a couple of classic quality defects. There are lexical defects. Do we all agree on what green means? To some people, green means the traffic light is green, I can go. To other people, it means it's eco-friendly. So what does it mean in the specific context? Syntactic, I saw the man on the hill with a telescope, can be interpreted in at least two ways. Either I had to use a telescope to see the man on the hill, or the man on the hill had a telescope. Semantic, all persons have a unique national insurance number. Does everybody have that one unique number? Or does everybody have their own individual unique number? Pragmatic one, the trucks shall treat the roads before they freeze. Who's freezing? The road or the truck? And then there's weak phrases, as soon as possible. It's better to put a specific deadline. And there can be omissions or generalization. Those are pretty close together. The syntax patterns we have learned earlier in this series are like the one down here, the ease template, when, under what conditions, the system shall, should, will, process something to be processed with more process details. So that will help avoid a lot of these linguistic quality defects. So if we try to improve the phrasing of these three requirements, what would you think? The system shall respond as fast as possible. Yes, weak phrasing. So be more specific about it. Students take 10 courses per semester. Students take 1,000 courses per semester. So does that mean each student takes 10 and overall they take 1,000? Shortly before the due date, the medium is extended unless somebody else reserved it. So for this one, we just have to figure out, did we have a reservation on the thing? And then when the due date comes up, can we extend it, yes or no? And by the fact of simply turning around that sentence, it will make it easier already. So to make it more specific, system shall respond as fast as possible. 90% of all cases, the system shall respond to all queries within 3 seconds. Second one, every student takes 10 courses per semester. And the third one, 3 days before the due date, the system checks whether the medium has been reserved. If not reserved, the system extends the lending period. Okay? All better understandable. For guidelines and checklists, what do you think? How would you write a guideline or a checklist for one of those artifacts? Try that. Put the video on pause. what are the criteria? Before you look back into the old assignment sheets where there is a checklist, I want you to think about what that checklist should be. And then finally, techniques for analytical quality assurance, checklists, quality gates, and Fagan inspections. One checklist by Lamsweerde, you remember that gentleman from goal modeling, is it must always be clear what, who, when, and where. And then there are defect-based criteria like contradictions, inadequacies, unmeasurability, unfeasibility, and poor structuring. And there can be quality-specific criteria. Is there any unspecified response in this operation to not receive an expected input value, or receiving it too early or too late? Does the logical OR of the input condition on this operation form a tautology? And we can come up with a lot more quality-specific criteria depending on how exactly we specify our requirements. Then there's domain issue-specific criteria, like what we typically face in a domain. Say automotive has different typical problems than, say, mobile phone engineering. Then we have content-related criteria, where we can check templates, did we fill the fields, were identifiers used consistently, are statement types correct, and then graphical notations. Data flow consistent, is the R diagram declaration correct, or we could check formal specifications. Quality gates then are another method to do this. These are defined in your process model. We talked about them early during the course, where for your context specification, your requirement specification, and your system specification, you have an initial milestone where you roughly know how it's defined, and then you have the final milestone where the specification is accepted. All of those milestones usually check the content, the documentation, and the accordance. So content, usual quality criteria, completeness, consistency. Documentation will check compliance with format, understandability, and ambiguity. And accordance will check if a requirement is agreed upon and if conflicts were resolved. Last but not least, Fagan Inspection. This is a structured process of trying to find defects in development documents, and it includes planning, overview, preparation, inspection meeting, adaptations, and follow-up control. Planning means a moderator plans a review process. In the overview, an author describes the background of the document under inspection. Preparation phase is that every reviewer examines the document in order to find defects. During the inspection meeting, a specific reader walks through the document chapter by chapter, and the inspectors point out found defects. For adaptations, the author of the document corrects the found defects according to the action plan agreed upon in the meeting. For follow-up control, the inspectors check whether the defects were fixed correctly. So remember the name, Fagan Inspection, maybe you can impress somebody. Other than that, remember the general process, because it works pretty well. And then finally, the IEEE 730 standard for software quality assurance processes. So in this figure, we see the relationship between the organization and the project, and we see that there is a software quality assurance framework that can be established, or that should be established within an organization. And then for each individual project, there should be a negotiated contract. And then we have software project planning, software project execution, and software project closing, all accompanied by software quality assurance processes and activities at the same time. When we create the product, we define the project processes along with that, the software quality processes and software development processes, through to the product lifecycle support and the end of life. And last but not least, this is how we derive requirements and relationships between the levels of the requirements. So from a contract, from the point of acquisition and then the stakeholder requirements definitions, we derive stakeholder requirements and process requirements. During system requirements analysis, we then get to the product requirements, and during software requirements analysis, we refine those into software requirements. And In this little overview table, we have the software quality assurance techniques just all listed in a little more detail. If you want to look into that standard in more detail, you will find a lot of very helpful activity detailing. And I'm just going to go through those process assurance activities so we also reflect on whether our processes already live up to what we want them to be or whether we need to improve the description of the actual process that we're following. So, finally, we looked at a couple of definitions for quality assurance and quality defects, for constructive quality assurance, guidelines and criteria, as well as reference models. We looked at analytical QA, quality gates, Fagan Inspection, checklists, and we looked at the IEEE 730 standard for software quality assurance. Thank you.